For decades, astronomers have relied on a simple rule when tracking comets. As they swing past the sun, they heat up, vent gas and dust, and then once that closest approach is over, they begin to calm down. Activity fades, energy dissipates. The object settles into a quieter phase as it moves away from intense solar radiation. That pattern has held true for almost everything we've ever observed, and that is exactly what scientists expected to see with 3I Atlas. After perihelion, the assumption was straightforward. The most violent interaction was behind it. Whatever internal stress the sun caused should already be resolving itself through outgassing and cooling. The models were clear. The forecasts were conservative. Nothing about the post-perihelion phase suggested escalation. But the instruments didn't follow the script. Instead of signs of relaxation, astronomers began detecting behavior associated with higher energy interaction, not brighter dust clouds, not lingering heat signatures. Something else entirely signals that point toward energetic processes becoming more pronounced, not weaker. The kind of behavior normally associated with intense interaction, not decline. That contradiction is subtle, but it matters, because comets don't usually surprise us after the hardest part is over. They don't suddenly look more active once the sun's grip loosens. And they certainly don't begin showing signs that suggest increased energy exchange when everything should be trending in the opposite direction. So now scientists are left with a quiet but uncomfortable question. If 3I Atlas has already passed its moment of maximum stress, why does it appear to be doing the one thing it shouldn't? Before this goes any further, one thing has to be made absolutely clear. When scientists say 3I Atlas is heating up, they are not talking about flames, internal combustion, or anything physically burning. Nothing inside the object is on fire. That would be the wrong picture entirely. What astronomers are seeing is something far more specific and far more telling. The signal comes from X-rays. X-ray emission does not measure temperature the way an infrared camera does. It measures energy. Specifically, it reveals high-energy interactions between charged particles and neutral atoms. In comets, X-rays are produced when fast-moving particles in the solar wind slam into gas released by the object, triggering a process called charge exchange. An electron jumps. Energy is released. X-rays appear. This phenomenon is well documented. NASA's Chandra X-ray Observatory has studied it for decades. ESA's XMM Newton has seen it too. We know comets can glow in X-rays, even though they are cold, icy bodies. There is nothing exotic about that part. What is unusual is when and how strongly it is happening here. X-ray emission usually peaks when solar interaction is most intense, near closest approach, and then fades as the comet vents material and moves away. It is a short-lived signature of peak stress. A flare, not a continuation. But with 3I Atlas, the energetic signal is showing up where the models predicted decline. Instead of tapering off, the interaction appears sustained, even amplified after the moment when activity should be settling. And that distinction matters. Because X-rays don't come from quiet objects drifting away. They come from systems still exchanging energy at a high level. Here is where the X-rays stop being a detail and start changing the entire story. X-ray emission from a comet happens through a process called solar wind charge exchange. In simple terms, the sun constantly fires a stream of charged particles outward at extreme speeds. When those particles collide with neutral gas around a comet, electrons jump between atoms. That jump releases energy, and that energy shows up as X-rays. This is not gentle contact. It is not passive glow. It is a high-energy interaction between a fast, aggressive plasma flow and material actively surrounding the object. When X-rays appear, it means the comet is not just drifting, it is engaged with its environment. Under normal conditions, this interaction peaks near closest approach to the sun, then it fades. As the comet vents gas and dust, its outer layers cool. The surrounding envelope thins. The solar wind has less to collide with. Energy output drops. That is the expected sequence. But 3I Atlas is not following it. Instead of weakening after perihelion, the energetic interaction appears to persist. In some measurements, it strengthens. That is the inversion that has scientists paying attention. Because post-perihelion comets are supposed to be running out of fuel, not sustaining high-energy exchange. We have seen another interstellar comet before. Borisov behaved exactly as expected. Its activity peaked, then declined smoothly. No sustained high-energy anomalies, no late-stage surprises. 3I, Atlas is different. It is not just emitting X-rays. It is doing so at a phase where the system should be calming down, and when energy output rises instead of falling, it forces a reassessment of what is actually driving the interaction. Because instead of powering down, the exchange appears to be intensifying. The problem is not that X-rays exist, it's when they are showing up. Comet physics is very clear on timing. As an object swings past the sun, heating peaks, volatiles flash off, and pressure is released. That release is supposed to calm the system. Gas escapes, dust spreads, the surface cools, energy output drops, everything trends toward decline. That is the rule. 3I, Atlas is breaking it. The X-ray signal is appearing after the moment when the system should already be settling, after peak solar exposure, after the most intense heating phase, at a point where venting should reduce interaction, not sustain it. Instead, instruments are seeing continued and, in some bands, heightened energetic exchange with the solar wind. That means the surrounding environment is not thinning the way models predict. There is still enough material, still enough structure, still enough interaction to keep producing high-energy emissions. That creates a timing contradiction. If the comet were simply venting normally, the X-ray glow should weaken rapidly. If it were passively cooling, the interaction zone should collapse. But neither appears to be happening cleanly here. This does not require exotic explanations. It does not demand speculation. It simply means the standard sequence is out of order. Energy release is persisting when physics expects decay. And when timing breaks before structure does, scientists stop asking what is happening and start asking why the system isn't responding the way it should. Because this isn't what comet physics predicts at this stage of the journey. This is where the conversation needs to slow down, not speed up. Despite the headlines, scientists are not talking about danger. They are not suggesting intent. They are not sounding alarms about threats. The concern is quieter, and in many ways more serious than panic. It is model failure. When astronomers see energy output increase where decline is expected, the response is not fear, it is recalibration. Comet models are built on assumptions: how gas expands, how plasma thins, how solar-wind interaction fades after peak heating. Those assumptions have held for decades across hundreds of objects. 3I, Atlas is pressuring those assumptions. The worry is not that something extraordinary is happening, but that something ordinary is happening in a way we do not yet understand. The geometry of the interaction may be unusual. The plasma environment around the object may be structured differently than expected. The surface or surrounding material may be sustaining charge exchange reactions longer than models allow. These are not dramatic conclusions. They are cautious ones. But caution increases when familiar equations stop predicting outcomes accurately. When outputs rise instead of fall, scientists do not look away, they lean in. Because unexpected energy behavior does not mean danger. It means the system is teaching us something new. And when the data stops matching expectations, attention sharpens. This is where the word alert needs to be understood correctly. NASA is not declaring an emergency in the cinematic sense. There are no warnings being issued, no countdowns, no danger scenarios. What alert means in this context is something far quieter and far more typical of how science actually works. It means heightened attention. Interstellar objects do not get treated like ordinary comets. They are rare, poorly sampled, and shaped by environments far outside our solar system. Every data point matters more. Every deviation carries extra weight. When an object like 3I, Atlas, shows behavior that strains existing models, agencies do not rush to conclusions. They slow everything down. More monitoring, more cross-checking, more modeling. That is what an alert looks like in real science. X-ray emissions are being tracked carefully. Solar wind conditions are being compared against simulations. Researchers are asking whether geometry, plasma density, or surface chemistry could sustain energetic interactions longer than expected. None of this implies threat. It implies responsibility. Because interstellar visitors are not just objects passing through. They are test cases, probes from environments we cannot recreate. If the models fail here, they may be incomplete everywhere. And that is why NASA is paying attention. Not because 3I, Atlas, is breaking the rules of the universe. but because it is testing how well we understand them.